Hi, my name is Charles Lee, and today I'm going to talk about curvature. From the previous lessons, we've learned that the vector value function r of t can be used to represent the movement of a particle. And we can use tangent vector t of t and the normal vector n of t to represent first the tangent direction of the particle and the vector that is normal to the tangent vector. And also, we have r prime of t equals v of t. V prime of t, v prime of t is a of t, which is the acceleration. And therefore, we can refer r prime prime of t equals to a of t. But the question is, the parameter t is not always the time in real life. It can actually be a function of time. The t here is a random parameter. It's arbitrary parameter. For example, if it's like t equals t naught, where t naught is the actual t in real life, the particle can be moving in different velocity. For example, it's moving pretty fast in this time period, but slow down in this time period. So the velocity is not uniform according to time. That's the problem. We have to find something that is easy to measure in order to investigate how sharp the particle turns. And how when we talk about how sharp the particle turns, we're actually trying to find the normal vector that is perpendicular to the tangent vector or the direction that it's going. For example, an or n of t. What parameter should we use then? Here we should use the distance s of t, which is represented by this formula, because it because the distance is actually easier to measure than the arbitrary parameter we have no idea about. If we take s of t and take the derivative of s of t as prime of t, we'll get the magnitude of r prime of t, which is r of s, which is r of s. It's not actually R of S actually. We can use it to get the magnitude of R of S because the magnitude of R of S is dr over ds, which is dr over dt times dt over ds. And by using this formula, we know that they are reciprocals. So if they multiply together, they get 1. So the magnitude of R prime of S is 1. That's the advantage of using S as a parameter. And we can get T of S equals to R prime of S over the magnitude of R prime of S, which is actually R prime of S, because the magnitude of R prime of S is 1. Also, we can use this to define the normal vector on T of S, which is T prime of S over the magnitude of T prime of S. And because T of S is actually having the magnitude of 1, which is because it's equals to R prime of S. So this actually equals to T prime of S itself. And what is T prime of S? It's actually R prime prime of S. Okay, so what does these vectors have to do with the curvature? Let's see this path that the particle is moving on a random path. It starts from P, which is S naught, let's say, and move to Q, having different tangent vector according to S. So an idea is that if you take 3 points on the path, there must exist a circle because the 3 points are coplanar and they're nonlinear since the path is curving. If it's not curving, then, well, we have nothing to investigate then. So as long as it curves, there must be a circle that goes through these 3 points. And if there is a circle go through these 3 points, if the points get closer and closer, we might get a tangent circle on a certain point P. With this idea, we try to find that if there is really such a circle. So let's see what a circle looks like. For a circle, let's investigate the easiest part. When the circle, it's centered at 0, 0, we can actually pull the idea of polar coordinates, which gives you c of theta equals r cosine theta. This represents the points on the circle. And if you take the derivatives, and c prime of theta, it has such properties. And what does these properties have to do with circle? Well, with the curvature. Well, examine this diagram. If we want to find the circle, then this circle must be on the line that is perpendicular to T of S. Also, it should be on the line that is perpendicular to Ts plus delta S, which gives you a circle that looks like this. Here, if we also use vector to represent this circle, then we actually have n of s on this direction, because from here we know, from here, or it's not working. Okay. From here we know that n of s is perpendicular because it's normal to t of s, because t prime of s is normal to t of s. Why? Because t prime of s has a magnitude of 1. So therefore, we can actually write the normal vector on it. And what's the next step? We try to represent this circle, the center of the circle, is equal to P times the magnitude of R, of course, because n of s is a unit vector, which is and the whole circle can be represented as so here. It turns out that if we take the Taylor expansion for the second degree of the vector value function, or here should be R of s, not R prime of s, but R of s. If we take the Taylor expansion we will get on s equals s naught, we will get this. Uh, and for c of s, we get e s naught plus plus. So what's the next step? We examine this theta here. Theta is actually here, it's theta s over r, which is s minus s naught over r. So c theta is actually c r theta s over r, which if you take the derivative, you'll get this. Therefore, if the circle wants to represent the vector value function, then we have to let c prime of theta having the same magnitude as r prime of s naught. And they're, of course, they're in the same direction if you calculate it. So therefore, r s naught equals to, and what's the magnitude of c theta? It's r. We get r prime of s naught equals to 1 over r. The magnitude of r prime s naught equals to 1 over r. If we want to use a circle to represent this path. So therefore, we can actually, when we examine the curvature, we are examining this. And what's the magnitude? And what's so special about this n prime of n of s? N of s is actually determined by t, which is r prime prime of s. And so here we get that its altitude is r 1 over r. So we can get the magnitude. With the magnitude, we can determine how sharp it turns. Using algebra seems to be a big abstract if we want to determine the curvature, but it's actually very accurate, and it's very, we can use it, but we can use this to prove by epsilon delta. But a simpler way to do this whole thing is, you see, we already found the circle. So let's examine this circle more closely. This circle, if we take t of s, the vector t of s, and the vector t s plus delta s, and also this delta t here. This is a triangle. This is a vector triangle. Next step, we took this vector, or like this side, which is r times n of s, course magnitude. Also that side, r times n, also the delta s, this is delta theta. Remember that t of s is always 1 because it's a unit vector. So therefore, we can actually get two similar triangles. As delta s approaches 0, they can be treated as a straight line. So these two triangles are similar because they're all equal at they have two equal sides, and these two angles are the same. So therefore, we can list the relationship equal to the magnitude of t of s is 1. R times the magnitude of n of s is r. Therefore, we get remember it happens when delta s approaches 0, so that we can use the similar triangle. So therefore, limit delta s approaches 0, the magnitude of delta t over delta s equals to 1 over r. What happens is delta s over delta s is of course r prime, sorry, t prime of s. Because we don't want a variable to be on the denominator, because well, if it doesn't curve at all, there will be no r, that r equals infinity. And also if it curves so much, r might become 0. So we don't want that to happen. We actually define 1 over r equals to k, the curvature. Why? Because if k goes bigger, that means r becomes smaller. And when r becomes smaller, you can clearly see when r goes smaller, when k gets bigger, you can clearly see r gets smaller and it turns sharper and sharper. So therefore, we explain where does the k, the curvature comes from, rather than just defining it as the magnitude of t prime of s.